My name is NUR'AINAA AQILAH binti FOAD.
Hi, my name is IZZATI binti MOHAMAD NOOR.
Hi, Assalamualaikum. My name is SHAHFIQAH binti SHAMSUL AZMI.
And my name is SITI HABIBAH binti ISMAIL.
Assalamualaikum warahmatullahi wabarakatuh. Today we want to present Mathematical Logic Chapter 2 and Chapter 3, which is Chapter 2 is about Argument and Quantifier, and Chapter 3 about Contraction Method and Math Induction. Today I want to present about argument. Argument is a list of given statement is called premise. For example, P1 or P2. Next, final statement is called conclusion, which is Q. This statement is valid if each other of the premise true and conclusion also true. This argument is valid by using truth table, law of logic, or rules of inference. There are 11 rules of inference. First one is smallest exponent, that the last one to eliminate the conditional statement by arguments. Second is law of syllogism, that statements are true like P implies Q, then we derive a true statement Q implies R. Third is modus tollens, is an application of the general truth that if a statement true that it is contrapositive. 4 is rule of conjunctive simplification, is eliminate one sentence where their main operator is and. 5. Rule of conjunction is adding to statement with character and. 6. Rule of disjunctive syllogism, having a disjunctive statement for one of its premise. 7. Rule of disjunctive application is adding statement with the character or number. 8. Rule of contradiction, the note that proposition cannot be both true and false. The method of proof assume if false as additional premise produce contradiction, conclude our assumption is false. 9. Rule of resolution is the two premises are said to be solved. 10. Rules of constructive dilemmas is a valid rules of inference or proposition logic. And the last one is rule for proof by case, is a mathematical statement that aims to exhaust all possibility by setting the problem into parts, so that the valid argument can be solved with the three solutions, which is its rule of inference, truth table, or law of logic. So the first solution is rules of inference. 1 until 3 is the premise. We must solve the statement until we get the answer is S. We can use law of rules to solve the question. The second solution is truth table. The answer must be tautology so that the statement is valid. The tautology that means all the answer must be true so that this is a tautology. Last solution is law of logic. This is example for question by using a law of logic. That's all for me about argument, and I pass to the next presenter. Thank you.
Okay, what is quantifiers? Quantifier is an operator that specifies how many individuals in domain of the source satisfies an open statement. What is open statement? Okay, so we can define a sentence that called an open statement if it contains one or more variables. Next, it is not proposition and is become a proposition with the variable in it are replaced by certain allowable choice. So quantifier are divided into two types, which are existential quantifier and universal quantifier. For existential quantifier, this is the symbol and this is the notation. exists x px. Next, px is true when for some x in the universe of the source. Then, if in the sentence have phrases like there exists x for some x and at least one x, it is called existential quantifier. Okay, next, for universal quantifier, this is the symbol, and universal x px is the notation. For this quantifier, px is true for every x in the universe of the source. We can found universal quantifier when we found the phrases like for all x and for every x in the sentence. Let's we talk about truth value. For example, the statement is Rx is equal to the x the power of 2 minus 1 more than 0. X denoted by all real numbers. Real number is any number from negative infinity to positive infinity. Okay, let's relook what the answer if the statement is for all x is x power of 2 minus 1 more than 0. So, the statement is false because if x is equal to 1, we put 1 into the equation. 1 power of 2 minus 1 is equal to 0. So, 0 is not more than 0. So, the statement is false. Next, we move to the next statement. If the statement there exists x is equal to x power of 2 minus 1 more than 0. Okay, just now we try when x equal to 1 is false. So we change x with another number. For example, x is equal to 2. The 2 power of 2 minus 1 is equal to 3. So 3 more than 0. So the statement is true. The next topic, which is negation of quantified statement. For example, given that for all x in px is equal to x is even number, then qx is equal to x power of 2 is odd number. Negate the following statement. Okay, before we negate the statement, we need to change the statement become a logical expression so that the statement will become like this. Universal x px implies qx. Okay, so let's negate this statement. First, we need to put negation in the statement. Then the negation universal x will become there exists x. Then we need to change the implies using definition of application. Then it will be negation bracket negation px or qx bracket. Next, we use De Morgan's law to separate the negation, and it will be there exists x, negation px, and negation qx. Then we use double negation rule to simplify the statement, and the result will be there exists x px and negation qx. So the conclusion is there exists x such that x is even and x power of 2 is also even number. About nested quantifiers. Nested quantifiers are quantifiers that occur within the scope of the quantifiers. Okay, let's redo some exercise about truth value nested quantifiers. The question is determine the truth value of each statement below. The universal set is the set of real number. Justify your answer by giving example or counter example. Okay. The first one, for all x, for all y, x power of 2 less than y plus 1. So the answer is false. Why? Because if we put x is 2 and y is 0, so we can get 4 less than 2. So that is false. Then the counter example will be x is 2 and y is 0. Next, if there exists x, there exists y, x power of 2 less than y minus plus 1, so the truth value is true. For example, x is 1 and y is 1. So if we want to get the example, we need to try. Okay, so that's all from me. So I will pass this video to my friends.
Okay, so next is chapter 3's topic. Okay, so the topic that I chose is the construction method. Okay, so before we go to the examples, let's just take a look at the context of this construction method. So, first, what is construction method? So, construction method is used when the conclusion involves an existential quantifier. So, basically there's two notations. The first one is there is, and the second one is such that. Okay, so when do we usually use it? So, the construction method can be used if the conclusion B is in the form of, okay, so the B basically needs to be in the form where there is an object with a certain property such that something happens. Okay, so next we're gonna look at the steps in the construction method. So basically there's 3 steps. The first one is identify object, certain property, something happens. Okay, the second one is construct the object. So basically we will use hypothesis to guess, procedure, devise an algorithm for procedure. Okay, so the third one is show that the object has the certain property and satisfies the something happens. Okay, let's move on to the example 1 for the construction method. Okay, so for the first questions, if s and t are even integers, then 4 divides 6s squared plus st squared. Okay, first we are going to find the analysis of proof. So for A, we're going to label it as s and t are even integers. And for B, it's going to be 4 divides 6s squared plus st squared. Okay, so for B1, we're going to turn it into 6s squared plus st squared equals to 4k, which k is the element of integer. Okay, for A1, we're going to use the definitions of even integers. So s we're going to be equals to 2a and t also going to be equals to 2b. A and b is the element of integers. Okay, so for A2, we're going to substitute s and t into the equations, which is 6s squared plus st squared. So it's going to be 6 in bracket 2a in bracket power of 2 plus 2a times 2b squared. Okay, for A3, it's going to be 24a squared plus 8ab squared. So we're going to factorize 4 to the front, take 4 to the front, so it's going to be 4 in bracket 6a squared plus 2ab squared. So we're going to let u equals to 6a squared plus 2ab squared. So the A4 is going to be 6s squared plus st squared equals to 4u, which u is the element of integer. So here, we're going to prove it that A4 is logically equivalent to B1. Okay, so let's proceed to the example 2. The question is, there exists a real number P such that for every real number Q, PQ minus 3P minus 3Q plus 12 will be equals to Q. then construct P. Okay, so for A, it's going to be PQ minus 3P minus 3Q plus 12 equals to equals to Q. And for B, it's going to be construct P. Okay, first for A1, we're going to substitute both sides with negative 3Q plus 12. So the answer is going to be PQ minus 3P will be equals to 4Q minus 12. For A2, we are going to factorize P to the front, so it's going to be P in bracket Q minus 3. So it will be equals to 4Q minus 12. So we are going to bring Q minus 3 to the right hand side. So it's going to be P equals to 4Q minus 12 over Q minus 3. So we are going to simplify it and get it, the answer of P equals to 4. So next, for B1, we are going to verify P equals to 4, satisfy PQ minus 3P minus 3Q plus 12 equals to Q. So when P equals to 4, first we have to substitute all the P into the equation. So we are going to get the answer is Q equals to Q. So the question is satisfied. Okay, so for the last example, so the question is prove that if x, y, and z are integer for which x divides z and z divides y, then x divides y. Okay, so for the analysis of proof, first we're going to label A as x, y, and z are integer for which x divides z and z divides y, and for B, it's going to be labeled as x divides y. Okay, so for B1, we're going to use the definition of divisible. So it's going to be y equals to ax, which A is the element of integer. So for A1, it's going to be the same, where z going to be equals to bx and y is going to be equals to cz. So B and C is the element of integers also. For A2, we are going to substitute z into y. So it's going to be y equals to CBS. Then we are going to put CB together. So it's going to be CB in bracket and S. So let U equals to CB. So A4 is going to be y equals to US, which U is the element of integer. So by these questions, it is proved that A4 is logically equivalent with B1.
So I'm going to discuss about mathematical induction. Mathematical induction is a legitimate method of proof for all positive integers n. Let Pn be a statement defined for integers n. There are 3 steps in mathematical induction. Step 1. Verify that Pn is true. Replace n everywhere in Pn by 1. Step 2. Assume that Pn is true. Step 3. Prove that Pn plus 1 is true. Start by writing Pn plus 1 and then rewrite Pn plus 1 in terms of Pn. For example 1, prove 3 power n more than equal to n plus 5 for all integer n more than 1. Step 1, show that P2 is true. So left hand side equal to 3 power 2 equal to 9. Right hand side 2 multiply 2 plus 5 equal to 9. So 9 more than equal to 9 is true. Step 2, assume that Pn is true. So Pn equal to 3 power n more than equal to n plus 5 for all integer n more than 1. Step 3, show that Pn is true. So left hand side 3 power n plus 1 equal to 3 power n multiply 3. So 3 power n plus 1 equal to 3 multiplied to n plus 5 using assumption. So 3 power n plus 1 more than equal 6n plus 15. So right hand side, 2 multiply n plus 1 plus 5 equal to 2n plus 7. So 6n plus 15 more than equal to n plus 7. Therefore, Pn plus 1 is true. Example 2. Prove that 1 power 3 plus 2 power 3 plus n power 3 equal to 1 over 4 n power 2 n plus 1 power 2. Okay, step 1. Show that P1 is true. So left hand side 1 power 3 equal to 1. Right hand side 1 over 4, 1 power 2, 1 plus 1 power 2 equal to 1. So left hand side equal to right hand side. P1 is true. Okay, step 2, assume that Pn is true. So Pn equal to 1 power 3 plus 2 power 3 plus n power 3 equal to 1 over 4 n power 2 n plus 1 power 2. Step 3, show that Pn plus 1 is true. So left hand side 1 over 4 n plus 1 power 2. N plus 1 plus 1 power 2 equal to n plus 1 power 2 n plus 2 power 2 over 4. Right hand side 1 over 4 n power 2. N plus 1 power 2 is taken from Pn plus n plus 1 power 3 is taken from the equation. Substitute n with n plus 1. And then n plus 1 power 2, n power 2 over 4 plus n plus 1 over 1. Okay, and then multiply n plus 1 with 4. Okay, and then n plus 1 power 2, n power 2 plus 4, n plus 4 over 4. Okay, and then factorize n plus 1 power 2, n plus 2 power 2 over 4. So, left hand side equal to right hand side. Therefore, Pn plus 1 is true. Example 3. Use induction to prove that 3 power n less than n plus 1 factorial for n more than equal to 4. So step 1, show that P4 is true. So 3 power 4 less than 4 plus 1 factorial. So 81 less than 120 is true. Step 2, assume that Pn is true. So Pn equal to 3 power n less than n plus 1 factorial. Step 3, show that Pn plus 1 is true. So 3 power n plus 1 equal to 3 power n multiply 3. 3 power n plus 1 less than n plus 1 factorial multiply 3. So take from the question 4 less than equal to n, 3 less than n, 3 less than n plus 2, and then multiply with n plus 1 factorial. So will be 3 n plus 1 factorial less than n plus 2 n plus 1 factorial. Okay, and then substitute into equation 3 power n plus 1 less than n plus 2 n plus 1 factorial. 3 power n plus 1 less than n plus 2 factorial. 3 power n plus 1 less than n plus 1 plus 1 factorial. Therefore, Pn plus 1 is true.
So for the last part, which is conclusion. So in order to improve one's quality of life, logic and proving are essential. There are proofs that can introduce a new technique for solving other problems in mathematics or provide insight into something that isn't related to the original content. We'll be able to widen our horizons in terms of what we know and comprehend. As a result, logic and reasoning are critical to remember and apply in order to get the best or most desirable outcomes.
Okay, that's all from us. Thank you for watching. Bye.